Hello everyone, my name is Tony Zlatinsky. I'm a GPU software engineer working for NVIDIA, where I'm a technical lead for Vulkan Video. I'm also one of the primary contributors to Vulkan Video specifications. The goal of this presentation is to describe the basic Vulkan Video core concepts, architecture, and APIs. We'll also look at the API from hardware perspective. Then we'll look at the parts used from Vulkan core, the add-on objects, and execution model. At the end, we'll touch on Vulkan video interaction and synchronization with the rest of the Vulkan video queue types, such as transfer, graphics, and compute, as well as application-specific use cases. The presentation assumes familiarity with Vulkan core APIs such as devices, queues, buffers, images, device memory, and synchronization. If you're unfamiliar with those concepts, I would highly recommend pausing here and reviewing those basic concepts using the previous Vulkanized sessions from this and previous years, as well as by reading the Vulkan specification. If you're not familiar with MPEG codec concepts, no worries, I'll introduce some basic concepts here. For further details, please refer to the H264 and 265 specifications. The ultimate goal is for you to have enough knowledge of Vulkan video architecture to go with, enabling the creation and optimizations of video applications utilizing Vulkan video APIs. This presentation is focused on video decode features. The features of the encoder will be covered in subsequent presentations after the formal specification is published. The Vulkan Video API was created with the following primary objectives: allow for video-enabled programs to be created once and used across several hardware platforms, have an efficient and low-latency integration with graphics, compute, and display, and allowing for scalability, targeting applications from embedded systems with very limited hardware resources to servers requiring high-throughput video processing. These diagrams describe the inputs and outputs required by the hardware decoders and encoders from a simplified architectural standpoint. The compressed bit stream is sent into a hardware decoder, which generates an image every frame and/or field. The encoder operates in the other direction. It accepts an uncompressed image and outputs compressed bit stream data for that image. If all you care about is decoding images in a simplified way, go ahead and download the video sample, the corresponding IHV driver, and start using hardware-accelerated AVC and HEVC decoding with Vulkan Video. Linux and Windows are currently supported on AMD, Intel, and NVIDIA hardware. FFmpeg and GStream are also adding support for Vulkan Video if those open source frameworks are preferred. Intel is adding support for Vulkan Video on their recent 11th to 13th generation CPUs, as well as the ARC GPUs. AMD will support RX 5000 and 6000 series GPUs. NVIDIA will enable Vulkan Video on all architectures, starting with Maxwell, including the most recent GPUs. Going back to video diagrams, modern video standards have a bit additional complexity that must be considered. The reference pictures, out-of-band parameters, the need to produce motion estimate data alongside the output, and so on. Why should one be concerned about reference pictures and out-of-band parameters? Because, as we shall see later in the presentation, controlling those resources may make a significant difference in throughput performance and memory use. Vulkan Video API is a low-level hardware API. It would be wrong to develop the API without taking the hardware into account. We have the simplified hardware decoder encoder block shown here, which will almost certainly include a hardware DMA queue to process the input data. When processing several streams in parallel, it also contains a memory context that holds configuration data, per stream and frame data, as well as safe restore memory and context transitions. What is the significance of this? We don't want to update hardware data context more frequently than it's absolutely necessary. In addition, we want to populate the per frame and stream data ahead of time. We don't want to be filling the data context while sending the operation request to the queue. Modern hardware can handle massive amount of bandwidth, 2 4K or 8 1080p streams or so forth. To fully exploit the hardware, the context should always be pre-populating the DMA memory, and the hardware queue must be kept as full as possible. We will see how Vulkan Video handles these requirements. This diagram shows the overlay of the hardware block with its context and the decoder's inputs and outputs. Let's now include to the diagram the corresponding Vulkan core and video objects. Similarly to the rest of the Vulkan queue families, we got in the middle the VK device containing some of the hardware context and the hardware queues. The video commands, along with the references to per frame and stream parameters, the input and output resources are recorded ahead of time in Vulkan command buffers. Those command buffers get submitted to Vulkan queues when work needs to be performed by the hardware. The input and output bitstream data is supplied in VK buffers backed by device memory. The reference, input, and output images are represented by image views that are backed by images and device memory, completely in control of the application. Individual and multi-layered images are supported. Please note that some implementations may only support image arrays for reference images. As with the rest of the Vulkan APIs, memory barriers and events are used for in-queue synchronization and layout transitions of resources. Queries are used for retrieving the status of video operations. Semaphores are used for cross and in-queue and host synchronization, where fences are used for synchronization with the host. Now we look at the new objects and commands introduced by Vulkan Video. Video decode and encode each come with their own command, VK command decode video and VK command encode video. The VK command decode video command is shown in blue on the left, along with the corresponding VK video decode info structure is added by the Vulkan Video Decode API. The hardware needs a place to store the per stream context when decoding and encoding multiple video streams. We could have designed the API to maintain the context within the Vulkan device itself, but then this would have required a new device to be created for each video stream. Each such device would have required the maintenance of a more state than was necessary for a single video stream. The overhead for creating and destroying a Vulkan device would have also increased. Instead, a lightweight VK video session object maintains only the compressed video stream state. As a result, video streams can be created and destroyed more efficiently and with less hardware resources. Some of the codecs require hundreds and even thousands of parameters to be configured for encoding and decoding. Some codec bitstream specifications introduced out-of-band data for the same reason. Set it once, use it many times within multiple frames and fields. To avoid setting these parameters with each frame and convert those parameters to a hardware-friendly format, we have the picture parameters objects. These objects maintain the parameters that are related to a portion or even to the entire video stream. The implementations have an opportunity to optimize the use of parameters data by converting and caching the parameters within these objects. And then we have the layered codecs extensions. For this example in the diagram, we have the H265 codec type in purple. Layering codec extensions allows for defining an extension per codec when implementation would advertise only the supported codec types. Domain-specific knowledge partitioning when developing applications. For the decoder, most of the codec-specific data comes from the parser. The rest of the video core API stays the same between the codec types. It also helps with IP separations. Khronos develops license-free royalty-free API, and the codec standards follow the corresponding licensing. Here's another representation of the hierarchical structure of the dependency of Vulkan video extensions to Vulkan core. On the left side, one could see Vulkan core. Of course, Vulkan video depends on all the core objects from the core, like Vulkan devices, Vulkan queues, images, buffers, device memory, synchronization objects, and everything else. Then in light blue on the top, the Vulkan video decode extension that adds the decode commands, along with on the right side in darker blue, the decode H264 and 65 extensions, which are already released. And at the upper right side in darker blue, you could see the future extensions that the video TSG is working on. Those are the Decode VP9 and Decode AV1 extensions. At the bottom, you could see the Vulkan video encode extensions. This is the core that adds the video encode commands, plus the corresponding H264 65 extensions that the video TSG is working on releasing very soon, as well as the later on, we're also going to release Vulkan video encode for AV1. Please note that as with any other Vulkan extensions, implementation can support one or many of those extensions. So application must actually check for support for any of the both decode and encode support, as well as the corresponding codecs if they are supported before trying to use those. And after determining the support for any of the extensions required, if the implementation supports video encode or decode and the corresponding codecs, then the first thing the application has to do is any other Vulkan applications is to create a Vulkan device. You should already know how to query the queue families from the physical devices to discover graphics, compute, transfer, and present functionality. So Vulkan Video adds those two additional types, video decode and video encode, where if you're looking for a queue with video decode functionality, then you're going to be looking for queue video decode bit set. And if you're looking for video encode functionality, you're going to be looking for the corresponding queue video encode bit set. As you're probably already aware, when physical devices advertise their queue family capabilities, usually they advertise multiple queue families support for a single queue. So for example, usually graphics all support transfer at least, and then most likely will also support compute, present, and so forth. When it comes to compute, it's also usually combined with transfer functionality. And then it's similar to video decode and encode queue types. Those at least are also going to advertise support for transfer functionality. And then some implementations may also support compute. If your application is required to use all the different queue types, graphics, compute, video decode, and encode simultaneously, go ahead and request the device to be created with all this functionality or all these different queue types. However, if your application would only need to use video decode functionality, I would highly recommend for you to create a device requesting only a queue type of video decode in the example below. This would actually save you system resources, and your device is going to be created much faster. This is a general principle that applies to all different queue types. Application should not create queues that is not planning to use. It will use additional system resources unnecessarily. Contemporary devices are capable of supporting multiple hardware instances of encoder and decoder. It's important to understand how many hardware block instances are supported by a physical device, in addition to whether it has the ability to encode or decode video. This information will allow the application to fully utilize the available hardware resources. The QFamily property's QCount property provides this information. When a hardware block offers significantly higher throughput than an application typically needs, an implementation may choose to advertise more queues than the actual number of physical device instances. In such cases, the implementation will context switch the work submitted to multiple queues created against a single hardware block instance. However, this shouldn't have an impact on how the API handles queue submissions. To repeat, when creating the Vulkan device, in the queue count field, only request the number of queue instances your program is actually going to use. This will prevent system resources from being wasted. Prior to decoding or encoding video, the application must create a video session object for each compressed video stream it intends to use. After creating the video session object, the application is required to query the object's requirement for device memory and then create and bind to that object the device memory required. Video session must be explicitly reset with video session reset command before its first use. After resetting the object, a video session may be reused again for additional compressed streams as long as the new stream is compatible with the previously produced object. The codec type, bit depth, and Khronos subsample of compatible object will be the same with the compressed bit stream. The parameters that were used to create an object, such as maximum number of references and the coded size, should likewise be compatible. Vulkan video profiles are structures used throughout the video-related APIs, describing the codec type and video format. VK video profile info structure is used for encoding physical device properties related to video. It is also chained to the corresponding resource creating structures that are going to be used with video operations. When creating Vulkan images, for example, the video profile is chained to VK image create info, and along with the video usage bits allows the implementations to optimize the image for the video operations. The VK video profile list info describes a collection of video profiles and is intended to be used for applications targeting transcoding. The plural version of this structure helps with the matching of the decoder output and encoder's input formats and image resources. When doing transcoding, we want the images that are used as an output to a decoder to be compatible with the images used as input to the encoders. Video session parameters contains the out-of-band parameters related to a portion or the entire compressed video stream. These objects must be created against the video session object. The API can add parameters to a video session parameters objects, but can't modify existing parameters with the same ID. However, there is a convenient API in Vulkan Video that allows for an existing object to be passed as a template when updating a new object. When the template object is provided, the new object will inherit all the existing parameters from the template, except the ones explicitly provided within the update list. This is the way parameters get overwritten in Vulkan Video in order to support concurrent and multi-threaded command buffer submission and recording. Before we talk about this picture parameters example, let me introduce some basic MPEG codec concepts. In MPEG standards, the network abstraction layer, or NAL, consists of series of NAL units. NAL units containing video coding layer, or VCL, is used for the coding slices, the data that the hardware decoders and encoders deal with the most, since those structures require the most time-intensive processing. Then there are also null units of type sequence parameter set, picture parameter set, and video parameter set, only found in HEVC. Those null units signal common control parameters to the decoder and are also referred to as non-VCL data. Sequence parameter set, SPS, contains syntax elements such as picture width, height, and bit depth. Picture parameter set, or PPS, contains information on entropy coding mode, slice groups, motion prediction, quantization parameters QP, and deblocking filters. SPS has an optional part that includes the video usability information or VUI parameters, which provide additional information about high-level properties of the video content such as aspect ratio, color space, chroma location, bitstream restrictions, timing, etc. Video parameter set or VPS, which only applies to HEVC, includes syntax elements for session negotiations such as profile and level. All VPS, SPS, PPS parameters are identified within the stream and referred to by the VCL layer by the instance IDs. This example represents a picture parameter object containing multiple VPS, SPS, and PPS entries. On the left, one can also see the implementation caching the post-process version of these parameters internally. In the process of discovering picture parameters with the help of the video parser, the application will add new parameters to a picture object. This picture object will be used with the video operations that refer to the VPS, SPS, PPS entries by their corresponding IDs. If the application detects a new parameter from the bit stream with an ID that already exists in the current picture parameter object, then a new picture object must be created since parameters are not allowed to be overwritten. The existing entries from the current object can be copied by the implementations to the new object when the existing one is passed as a template during the parameters update. A NIF application design would allocate a single command buffer, record the video commands, submit the buffer to the video queue, and then using a fence will wait on the device queue to complete the decoding operation. Then, by reusing the command buffer, the application would complete the same sequence for the next frame. This design would very negatively affect the performance of the video solution. A significantly superior design would allocate as many command buffers as the queue's depth effective items. The deeper the queue, the greater the processing throughput, and the greater the resource requirements, because for each active entry in the queue, the application will have associated resources. Also, the deeper the queue, the greater the number of decode frames that must be resubmitted in the event of error during decoding. The data in bitstream may be malformed due to network transmission problems. When using status queries, the application can determine if there were errors during decoding and take appropriate actions. Most of the decoders will try to recover from errors by producing acceptable decoded picture output. However, sometimes this may not be possible. In such cases, the frames would need to be resubmitted, perhaps in a different order, starting with a better reference such as a keyframe, for example. Using several host threads would be an alternative method for recording command buffers. This design is more complex, but would utilize CPU resources more efficiently. If, for instance, a CPU has 16 threads, it may concurrently record 16 command buffers, serialize the frames in decode order, and send them to the video queues. When semaphores are used, the decoder will continue to handle the decode video queue until all frames has been decoded. This would allow the host CPU to sleep or perform other tasks rather than serving the queue events with every frame. This strategy has been shown to result in a significant energy efficiency. FFmpeg goes a step further by using multiple threads for parsing the content in addition to recording the command buffers in Vulkan. As previously stated, submitting command buffers containing video decode or encode commands is not different than any other video command buffer submissions. One or more recorded Vulkan video command buffers can be submitted. The command buffer sequences can be synchronized by binary or timeline semaphores, and the command buffer sequences can be synchronized with the host CPU or between the Vulkan queues via semaphores or a fence. Let's now go a level down and look at the video decode and encode command themselves. All Vulkan video command sequences start with VK command begin video coding and end with VK command end video coding. A command buffer may have multiple begin-end video command sequences. Transfer operations are also required to be supported in video queues. There is an implicit ordering of the commands in the same command buffer, so when submitted, the commands are guaranteed to be executed in the recording order. Going one more level down, VK command begin video coding establishes the context for the subsequent video commands. VK command begin video coding along with VK video begin coding info would select the active video session object and picture parameters and is going to set the reference picture resources in slots. VK command end video coding terminates the context established by the last VK command begin video coding. Here are the only commands which are allowed between VK command begin video coding and VK command end video coding. The most significant commands, of course, are decode and encode operations. As previously mentioned, transfer operations are also required to be supported. Please note that bleed operations are not regular transfer operations, so they are not supported by the video queues. Video queries are also supported, and for the decoder, they are used to obtain the status of the decode operations, and for the encoder, they are used to get the sizes and the offsets of the bit stream generated. Memory, buffer, and image barriers and layout transitions are also supported. Application is required to correctly transition the layout of image resources and use memory barriers per the specification. In Vulkan Video, all resources, including images necessary for references and DPB slot indices, are explicitly managed by the application. One may think of a DPB slot indices as a null-based array of hardware slots to which an application can assign image resources and then use these indices to refer to picture references. This is depicted at the bottom left corner of the diagram. Internally, in the video session object, the implementation may have a DPB slot state associated with the references. This state will also likely contain some codec-specific information. This state can also have an internal weak reference to the image associated with the slot. When creating image resources for picture references, the application is required to indicate its intended use with image usage video decode DPB and or image usage video encode DPB image usage flags. This allows the application to set up the image for use as a reference and potentially associating implementation-specific video session-dependent metadata. Applications are also free to associate any state with such picture references. Both individual and image arrays are supported. However, please note that some implementation may not support individual images for references. Please make sure to query the video capabilities for video capability separate reference images flag before using individual images. When using image arrays, each image array layer represents a single reference. Please note that image array layers and DPB slot indices are completely independent concepts. So it is possible image array layer 5 to be associated with DPB slot index 8, for example. When a new reference is required, since the video parser indicated that decoded image is to become a short or long-term reference, or a new reconstructed image is going to be required for the encoder to use in following frames, the application must create such references by A. Allocating a DPB slot index, B. Allocating the image resource, image view, and bucket memory for it, and C. Submit the pair of DPB slot index with the associated image view to a decode or encode queue in so-called setup slot. After the decoding or encoding operation has been successfully executed by the video queue, the DPB slot index and its associated image become a valid reference that the application may use with the following frames. Application, possibly with the assistance of the video parser, determines how long this reference will be considered valid. Here below are the rules to invalidate and reassociate DPB slots. Here is an example of managing DPB slots with image references for a video session. On the left side of the diagram, you could see slot ID indices from 0 to 6, because this specific content requires only up to 7 references. As a side note here, while creating a video session, the program will waste memory resources if it overallocates the number of DPB slots by setting bigger values for max DPB slot and max active reference pictures than its intended number of references to be used with the targeted content. Since this example is starting command buffer recording at the beginning of the compressed content, there are no reference images created yet. The example is intending to record a command buffer with 7 and then 6 decode operation sequences grouped together between command begin video coding and command end video coding. As stated before, within the command begin video coding command, the application is required to declare the reference images it is planning to use in VK video begin coding info. In this example, we're using an image array where for each reference we're using a layer index shown in blue. The application has located and specified in the reference list for the first sequences of decode commands that it is going to create and use a total of 4 references with the image layer number 1, 12, 2, and 5. All these references will have their corresponding DPB slot set to -1, which means those references are still unallocated and therefore invalid. Each recorded decode command will process one frame and generate one valid reference, except for frame numbers 3 and 10 highlighted in yellow above. Within these 2 frames, the decode operation will produce an output image, but it will not generate a reference. So, you could see that frame 1 will specify its setup slot, image layer index 1 with slot index 0. After the decoding of this command, this pair will be considered a valid reference that the subsequent commands can use. Frame 2 uses image layer index 2 with slot index 2 in the setup. Frame 3 uses image layer index 3 for its output image, but it did not set up the image as a reference. So this command will produce an output image, but will not generate a reference. This example also demonstrates the invalid usage in Vulkan video, where in frames 6 and 7, the sequence was attempting to use image layer index 4 to associate with slot index 0. However, since in command begin video coding reference image layer index 1 was specified and slot 0 was already associated with this image in frame number 1 in the same begin end sequence, it is invalid to overwrite the slot with a new image in this sequence. The corrected setup is showing the next begin end sequence where image layer index 4 was explicitly specified to become a reference in video begin calling info. So after frame 7, shown in this example, DPB slot 0 gets reassociated from image layer index 1 to 4. After frame 7, image layer index 1 is not a valid reference anymore. Please also note that when specifying the references for image indices 12, 2, and 5, the previously associated slot indices must be specified in video begin coding info, since those now represent the valid references. The same DPB management rules apply when multi-threading command buffer recording is used. In the case of multi-threading, it may be necessary for resource allocations to occur within the thread dispatcher to ensure proper execution. In this example, each thread records only one frame per begin-end coding sequence. Most of the image layout transitions in Vulkan apply to Vulkan video as well. However, there are some special implicit image layout transitioning use cases. Specifically, video images are considered to be an undefined layout not only after they have been created, but also when used for a first time with a video session that has been reset, or the compressed video content size or other image layout affecting parameters were to change. Video queries are used to obtain the status of video decode and encode operations. In Vulkan video, the host side VK get query pull results function is used to obtain the status and results for a set of queries. The device side VK command copy query pull results command that copies the results from the queries to a buffer is currently unsupported in Vulkan video. To determine if a video decode command completed the decoding operation successfully, use the result with status query type. And to determine the size and the offset of the output bit stream within the output buffer when using the encode commands, use the video encode bitstream buffer range query type. Different implementations support a variety of codec types, capabilities, and image formats. Use the corresponding physical device functions to determine the capabilities and limitations of the encoder and decoder devices for their proper use. Most of the video codec operations are universally used within the different IHV implementations. However, for the decode output specifically, there are two different modes that different hardware implementations can support: DPBN output distinct and DPBN output coincide. Use the video decode capabilities flags to determine if the output and reconstructed picture coincide or separate image resources must be used for the output of the decoder. Let's now look at some specific Vulkan video configurations and application usage. Remember that a physical device implementation may have one or more video decoder or encoder hardware block instances. If multiple instances of a hardware block are available, the application should consider load balancing across these hardware resources in order to maximize the system's capabilities. After creating a Vulkan device with multiple video queue instances, the application can use vk-get-device-queue with the corresponding queue index to get the queue for the respective hardware device. These queues, representing different hardware blocks, can then be used across multiple streams to better utilize the device. These same configurations can be used with multiple streams, multiple threads, and multiple processes. If you are planning to share a queue across multiple threads, ensure to synchronize the submit operations to it, since according to a Vulkan specification, Vulkan queues must be externally synchronized. Here is another load balancing configuration that Vulkan video applications can use. If your application requires very heavy video processing operations, like 8K main profile or low latency, the processing of a stream can be split across multiple hardware instances. If there are dependencies between the video queue submit operations, which is usually the case when using references, the application can use Vulkan semaphores to ensure proper ordering between the queues. One timeline semaphore or a pair of weight signal binary semaphores per queue can be used to ensure the dependency between the video operations. If there is no dependencies between the queue operations within the stream, then no semaphores use will be required. With very little reorganization, these multiple queue configurations give the Vulkan video applications tremendous power. Let's now look at the interaction of the video decode queues with the rest of the video queues. One of the simpler configurations, not requiring more advanced graphics or compute frame transformations, would be to submit the frames directly to a display presentation queue after the frames have been decoded by the decode queue. Vulkan synchronization primitives such as semaphores or fences can be used to ensure the video operations are completed before the display starts using the images. This configuration assumes the decoder's output is compatible with the type and the layout of the images that the display can consume. Please note that the order in which the frames are submitted to a decode queue may or may not be the same as the order submitted to a display. When using compressed video, there is the concept of decode order, in which the frames are submitted to a decoder, and then there is a display order, in which the frames are submitted for presentation purposes. Using Vulkan semaphores and present time extensions simplifies the applications and improves the performance and the latency of the presentation. In that case, the application video frame dispatcher would submit the frames to the decode and present queues in appropriate order, and then rely on synchronization to display the frames when decoded and at the appropriate present time. Managing the presentation with fences and without the present time extensions would require more complex host handling of the frames, which usually result in a lower visual performance and incorrect video synchronization timing. Most of us have seen video played at unusual speed where the sound and video pictures do not coincide in time. Here is a high-level architecture of a bit more complex video application configuration, where the frames decoded from the video decode queues are passed to the graphics queue for more powerful graphics, post-processing, and/or color conversion before being displayed by the presentation queue. There is a YCBCR sampler conversion extension in Vulkan that allows for YCBCR images that are output by the decoder to be directly fetched by the texture sampler. This reduces the overhead of the processing video frames by the graphics to minimum. Again, with this configuration, when using Vulkan semaphores, the design of the application is much simplified, where the application video frame dispatcher would submit the frames to a decode and then write the way to the graphics and present cues in the appropriate order. This setup relies on Vulkan synchronization to display the frames when decoded and graphics processed at the appropriate present times. The Vulkan video sample application is processing the frames using the same architecture. The decoded frames are converted to RGB color space using YCBCR sampler color conversion extension and then scaled to always fit the display size independently of the video content and display resolution. Before we start looking at the timing diagrams, I would like to clarify a few things about the synchronization in Vulkan. There are two types of semaphores in Vulkan, timeline and binary semaphores. Timeline semaphores can be used by the host to wait on, which is the same as using it as a fence. There are also other ways to wait on device queue work from the host, in addition to waiting on a classical fence objects, like waiting on queries and events. When referring to fences within the next diagrams, this would apply to all the CPU host synchronization methods. When referring to semaphores, only Vulkan device queue-based synchronization is considered. Let's now look at the diagram where work is being submitted and synchronized solely by the host CPU. For each queue submission, the CPU is waiting with a fence or query for the fence to be completed. Then the host submits and waits for the graphics work to be done, and finally, it does the same for the presentation. There is queue submission overhead and latency involved when dealing with device queues, which are essential facts to keep in mind. When the host waits on system events to process the fences, there is an overhead of serving those events. Then there is a latency caused by the host work that needs to be done before the submission and the overhead of submitting work to the device itself. So even though the compressed stream is available and can be processed at a high rate, when only using fences to handle work, there are these big gaps between the queue work. There are other consequences because of the latency of submissions. Since the display usually works in synchronous mode, it will start missing decoded frames more frequently, and this will be noticed by the user in the form of the lower and inconsistent presentation rate. In this case, the video decoder, the graphics, and the display work in a lockstep, causing these devices to be constantly active, causing more energy use than necessary. The throughput of the device gets further reduced because not enough work is available for it to handle. In addition, most likely the power management system would detect the sporadic and inefficient nature of the available work submitted and would therefore slow down the clocks of the hardware, further reducing the throughput and energy efficiency and increasing the latency of the solution. As we shall see later, due to the decode display ordering, the latency issue is significantly worse than depicted here. Here is a timing diagram for the same configuration of the application from page 35, but this time using solely Vulkan semaphores to synchronize work between the device queues. The application's work dispatcher in this case submits frames to the decode queue in decode order, one after another without waiting by the host for the work to be done by the decoder device. Instead, it relies on semaphores to ensure that the graphics work does not start processing the output images before the decoder is done processing the frame. The dispatcher also submits work in display order to graphics and then to a display right after, again relying on the semaphores to ensure proper synchronization of the frames. One can see from the diagram that the throughput is much higher with this solution and the latency is also much better. The primary reason for that is that a lot of work gets submitted to a device queue and being waited on in the device side hardware to be signaled. After the work becomes available, the device will start processing the work almost immediately. There is no round-trip processing going through the host. Since the decode and graphics queue operate at a significantly faster rate than the display, there is little to no risk of the display missing frames. Those frames are waiting at the presentation queue and when become signaled, get displayed with the next vsync tick immediately. Also, because of the high burst packet rate of the work by the host, the decoder, and the graphics, these devices can process all these bursts of work for a very short time and then be placed in a lower power. Or these devices can switch on handling other pending work. This increases the power efficiency and concurrency of the solution. The size of the work items in the burst are driven by the application's queue size and available system resources. This approach is not perfect, however. What happens with all these decode frame submissions if there is a frame with unrecoverable decoder error? In this case, the frame must be excluded from the presentation. Unfortunately, there is currently no solution for that. However, we're looking at ways to propagate the decoder status, considering it within the subsequent processing stages, where the frames with error status can be skipped or display can reuse the previous frames. In the meantime, we would rely more on decoders to attempt frame recovery and have more complex application solutions to skip or repeat frames at the display site. One may have noticed that this diagram handles a compressed stream with IMP frames only, where the decode and display ordering is the same, making the solution much simpler. In reality, most of the contemporary compressed content will have a more complex group of picture structures containing B-frames in addition to intra and predicted frames. B stands for bidirectional frames because these frames are constructed using not only past but also future references. This type of display ordering increases the latency of display pipeline because multiple frames would need to be decoded before being displayed. This further necessitates the requirement for using higher throughput and low latency processing solutions of the decoded frames. All these diagrams were captured with the help of the NVIDIA Nsight graphics and system profiler. Please use the links below to look at the different tools that NVIDIA offers to help with the development of Vulkan applications and specifically also supporting Vulkan video applications. Using these tools, one can very easily debug their Vulkan video applications by looking at the timing, looking at the input, output, and reference images. The video content has frame rates that is usually different than the one of the display pipeline. Video content can have a frame rate from 15 to 120 fps, where a display can have frame rates from 3060 to 360 fps. Contemporary displays also support variable presentation rate. It is the video application's responsibility to ensure that the video content is at the targeted present rate and it's also well synchronized with its corresponding video soundtrack. The different timing characteristics of the display and the decode and graphics pipelines pose challenges to achieving well-designed video presentation timing solutions. In this specific example, the video frame rate is 30 fps, but the display rate is at 60. If the application is not taking care of the presentation timing, the video will be incorrectly played at double the frame rate, being completely out of sync with the soundtrack. The application can try to control the timing of the frames submitted to a display, but getting the right timing, considering the characteristics of the different display types, would be very challenging. This is where the present time extensions come to help. VK Google Display Timing and VK EXT Present Timing both provide accurate display timing and, more importantly, allow for frames to be submitted in present at time mode. The application indicates at what particular time the frame must be presented. The frames are being queued to the display hardware and presented only when the time specified by the application has elapsed. These extensions also provide feedback on what the last presentation time was, giving the opportunity of the application to further adjust its timing. Unfortunately, Not all devices support VK Google Timing extension, and VK Present Timing is still under development. Please help encouraging the developers of VKXT Present Timing extensions to release it soon, since the display timing is an essential feature for delivering good quality video application solutions. When using a display timing extension, the application will request the frame present time when submitting it to the present queue. The present queue will skip displaying frames until their time requested by the application has been reached. If you were to compare this with the previous timing diagrams, the video content will now be displayed at the targeted display rate. Let's now look at how does Vulkan Video supports high dynamic range. First, HDR has a lot of standards. HDR10, HDR10 Plus, Dolby Vision, HLG and others. Then there are standards like ST2086, 2094, 2094-10 and so forth. Some of these standards require HDR configuration data to be set once, also called static metadata. This mode is used by HDR10. That basically means that the metadata is sent to a display at the beginning of the scene. Others, like Dolby Vision, can set metadata with each frame. Some of the HDR metadata relates to a display device, while others relate to the scenes in the content that's transmitted alongside the compressed video stream. This HDR metadata description and its specific use goes outside the Vulkan video specification scope. The HDR relevant aspect of Vulkan Video is its support for 10 and 12-bit depth, which it provides. Also, some of the HDR metadata is directly handled by the display supporting HDR. For content that is handled by the graphics, here's an example of how this can be done in Vulkan. The application, with the help of the parser and the display configuration data, would extract the static and dynamic HDR configuration metadata according to the HDR standard, and then would send this data to the graphics stage along with the decoded frames to post-process the decoded stream to desired authored content. Further HDR metadata can also be sent to a display. Various content providers and solutions handle protected content in a variety of ways. One of the ways for dealing with protected content in Vulkan is by creating a privileged service where protected memory resources and queues are used, a feature available in Vulkan. An important aspect of protected resources in Vulkan is that those can be accessed by the host and can be transferred to other unprotected resources. Within the protected service, the application would create as protected all device queues, memory, buffer, images, and command buffers. After decoding the video content using the protected decode queues, the frames can be sent to the HDCP enabled display for presentation. An alternative to using privileged protected service would be to use encrypted keys directly with the decoder device. The decoder in this case would decrypt and then decode the compressed video stream. This solution would still require the use of protected resources and queues in Vulkan. At this point, however, the ability to decrypt the content using encryption keys before decoding the frames would require a vendor-specific extension. The application is in control of the memory resources in Vulkan Video. Here are the ways the application can control the memory resources. The application has at least two options when it comes to dealing with the content stream resize. One option would be knowing the maximum stream size and number of DPBs. One can create a session with the maximum parameters required for the entire stream. This would imply the usage of more memory, but the latency will be lower. Or option 2 would be to create a session with the minimum parameters required for the current state of the stream, and then when the size changes in the way to require a bigger resolution or more number of DPBs, then a new session will be created and the old one will be destroyed. This would imply a little bit of overhead on switching from one session to another. The application also has control over at what point of time it would need to allocate bitstream buffers input, output, and DPB images. After the application is done with the buffer image resources, it may decide to completely free those resources or strip those out of the physical memory backing if sparse memory is used. When creating images that will be shared by many queue types, such as decoders, encoders, graphics, compute, and display, the application is equipped with the necessary Vulkan tools to ensure that these images are compatible, hence eliminating the need to copy images between the processing stages. This reduces the memory requirements and bandwidth usage, as well as the latency of the solutions. Vulkan supports sparse buffers and images, and so are the Vulkan video implementations. This is yet another way to manage memory sources. When the sparse memory is used, the application can partially or completely remove the memory backing from these resources instead of creating and destroying the buffers and images themselves. These diagrams puts emphasis to the way the video content can be resized without relocating the Vulkan images. Images are allocated with the maximum content size. When decoding the video frames, the application is providing information about the coded size for each decoded frame. The decoder would only use the area of the Vulkan images that is relevant to the coded pictures. When processing the images with the graphics or compute, the application will need to take care for only the relevant content to be displayed. This is the way the current resize feature is implemented in the sample app. The conclusion of these presentations are: Vulkan Video Extension is powerful cross-platform API. It provides a ton of flexibility in building scalable, performing, and highly configurable video applications, and the API is supported by open source implementations by major IHVs. On this page, you could find a list of references you may need to access the Vulkan specifications, SDKs, Vulkan loader tools, and drivers. You're welcome to join the GDC conference, where there will be even more talks about Vulkan, Vulkan Video, and other exciting technologies. Please feel free to join the NVIDIA's development program, where you could get access to tools, training, and support from the community.